Hello there, this is Rupesh and you're watching CPNet's video series on C++. And in this video, we'll be learning about what are the bitwise operators. So before this, we learn about relational operators, logical operator. So let's go ahead and study what is this binary AND operator. So first of all, we'll be learning what is this AND operator. Okay. So let's first talk about what is the bit operation. So in left hand side, I'll write the binary of 0 to 7, like 0, 1, 2, 3. So the binary of this one is 0, 0 and 0. 6 is 1, 1, 0. Okay. So this is the binary representation of respective numbers here. So we'll be understanding this video on the basis of these binary numbers and these numbers. Okay. These are the decimal number. This is decimal. This is binary here. Okay. And we're going to learn this bitwise AND operator. Okay. So if you are writing AND operator like 1 and 1, then what it will do, as it is bitwise AND operator, it will take bits of A. So what is this A bit? 0, 0, 1. See this one. And it will apply the AND operation on the same thing. So AND operator work like this. This 2 should be 1 in order to produce 1. So the rules for AND operation is 1 with 1 is 1. So this true with true is true. It's something like this. So this is binary, okay, not this decimal. So this one is 1 bit and another one is 1 bit. So 1 bit and with 1 bit produce 1. So if it is 0 and with 0 it produces 0. If it is 0 and with 1 produce 0. If it is 1 and with 0 produce 0. So remember this, 1 will always come when both side 1 is there and we are using this bitwise AND operator. Okay. So as we all know what is the meaning of AND. AND tells I want this side and this side true in order to produce true. Okay. And we consider 1 as true and 0 as false. Okay. So this is our rule set. Okay. For AND operations on bits. So this is 1 bit, this is 1 bit, this is 1 bit, like this. So this is not a decimal, this is a binary bits. Okay. And these are the outcome of these operations. So we were talking about what is 1 and with 1. So the result is 1. So we'll be writing 1 here, 0 and with 0, 0, 0 and with 0, 0. Okay, you can check it here. Got it? So if you are writing it like inside some if, this is 1 and this is 1. So 1 and 1, and you will be allowed to go inside this loop because this is producing 1 here. And let me tell you one thing, if you are writing inside if, and if you don't know, you will be surprised to know about this. If you are writing anything in your if, you would be allowed to go inside like this. If you're writing here, whatever, like -1, 1, 10, 1000, or A, or C, or D, whatever you want to write, if you're writing inside this, you will be allowed to go inside if, because all the values are considered true. The only thing which is not considered true is 0. So if you are writing 0 here, this is false. Other than that, whatever is coming inside if, that is true. Okay, so here this 1 AND operation with 1 would result 1. So this would be replaced as 1. So as this is a non-zero value, this if statement is evaluated as true and you will go inside if. Okay. So this is how it works. So let's take some another value like 3 and with 7. So 3 is nothing but 0, 1, 1 and 7 is 1, 0, 0. So we are going to perform AND operation. So we know the rule, 1 with 1, 1, 1 with 1, 1 and 0 and with 1 is 0. So this is 3 and this is a non-zero value. So if you have written this expression, it like if 3 AND operation with 7, you would be allowed to go inside this if, okay, because this is producing 3 here and 3 is non-zero, so you would be allowed to go inside this if. So this is how this AND operation work, okay. So let's go for the bitwise OR operators. So this is your binary OR operator. So how would you use that? So let's first write the rule for this. So if you are applying binary OR with this 0 and 0 bit, the result will be 0. And if it is 1 OR with 1, it is 1. 1 OR with 0, 0 OR with 1, it is 1. So it is 1 whenever there is at least one bit in your operation, okay. So it is exactly the opposite of your AND operator, okay. So let's check this out. So if you are writing expression like if 1 or 1, so let's see what would be the result for that. So don't get confused with this. This is an OR operator and this is 1 and this is 1, decimal 1, okay. So as this is a binary operator, this will perform binary operation on 1 and 1. So 1 is this and this is this. So this OR operator would result in 1 1 with 1, 0 and 0. So as this is a non-zero value, this would replace as 1, and if it is non-zero, you are allowed to go inside your if statement, okay. So this is how it works. And let's take another example like 4 OR with 0. So 0 is 3 times 0, 4 is 100. So OR with 0 0, the rule says 0 0 0 0 0 1 1. So the result is again 4 here, which is a non-zero quantity. So this expression is evaluated as true here, okay. So this is how this OR work. So let's look at the next one, which is this binary XOR operator. So this XOR operator is little bit difficult to understand, but let's give it a try here. So this is the sign of your XOR operator here, okay, this particular sign. So we'll write the rule here for 0 XOR with 0, 0 XOR with 1, 1 XOR with 0 and 1 XOR with 1. So the rule says if both are equal, like either 0 0 or 1 1, it produces 0, and if both are different, it produces 1. So this is the rule for XOR operation, okay. You go ahead and see in your book, you will get this, okay. So the same thing for any operation like if 1 XOR with 5, this would result in 1 means 0 0 1, 5 means 1 0 1. So 1 1 produces 0 in XOR, so this will be 0. So both are 0, so I mean both are equal, so it will again 0. Both are different, then it will be 1. So as this is a non-zero quantity, because this is 4, so this expression will be evaluated as true here, and you would be allowed to go inside your if statement, okay. So this is how this XOR operation work. So this is the rule for your XOR operations, okay. Now another one is this binary ones complement. The use of the binary ones complement is like this. The symbol is this one, and the rule for this is like this. If this is applied on true, result will be false, and if this is applied on false, then result would be true. So if it is applied with 0, the result would be 1, and if this is applied with 1, the result would be 0 here, okay. So this is the job of this one. So these operations are always on binaries, okay. So if I'm talking about these operations, always performing on the bits, okay. So 0 bit will become 1 and 1 bit will become 0. So if you are writing it like this one and 1, so notice this is a unary operator. You are not writing it like 1 and 2. No. Before what we learned, that AND operator, OR operator and XOR operator, those operators was binary operator. Like for this you need have left hand side and right hand side, left hand right hand side, left hand side, right hand side. But for this one, particularly for this operation, you don't need left hand side and right hand. you need just one expression. Okay, so this expression could be anything like if negation, and here you can have 1 and 2. Okay, so this will get evaluated like 1 and operation with 2. So 1 is nothing but 0 0 1 and 2 is 0 1 0. So you are going to perform this AND operation, which is nothing but 1 0 0 0 1 0 0 0 0. So the result is coming as 0. So this whole expression from here to here is producing 0. 0 is false value. So as I told, false applied with negation, which is binary ones complement, which does the complement. So whatever is there, it will reverse that. So if it is false, it will make it true here. Okay, so if it is false, it will make it true here. So this whole expression will be evaluated as true and you would be allowed to enter. Okay, but notice this, for this to work, there is only one value, right? This one was expression, so this expression get evaluated and resulted into either false and true, and we are feeding that false and true into this operator. Okay, so this one will be like true only because this one is having 0 0 1 and you are applying this inverter. We can call it lots of things. Okay, so this is a complementer, so it will complement or it will invert everything because it is one's complement. So one's complement does the reverse thing, it will make 1 as 0 and 0 as 1. So this is the result. So as this is a non-zero quantity, actually this is 6. So if you are writing 6 here, which is a non-zero quantity, so you are allowed to go inside that because that is not 0. Okay, if it is producing 0, then only you are not going to enter in. Okay, so we are left with this binary left shift and binary right shift. So let's try to understand binary left shift here. So this is the symbol for binary left shift. So what is left shift? So let me tell you something about your computer. We all know when we write integer v is equal to 10 here, there is some place in memory called v and we are storing 10 into that. So how that thing actually work? So let's try to understand that. As we tell, we are creating integer type. So this integer type is having size as 4 bytes. So if you don't know what is byte, let me tell you, 1 byte is equal to 8 bits. Okay, so if you are writing consecutive 8 bits like this one, this one, this one and this one, this is like 4 and 4 8. So this is 8 bits, which is nothing but 1 byte. Okay, so this could be anything like 1 here, 0 here, but the main point is the numbers should be 8 times. So 8 bits are total bits are 8 bits, that's why it is called 1 byte. Okay, so if it is 4 times, then it is 4 byte. So you can assume that if you are creating variable v as integer which is of 4 byte, so it will be taking memory in your RAM. How much? 4 times 8 bits. So how many bits will be there? 32 bits. So you will be taking from 0 to 31 bits in your memory, which is nothing but your RAM here. Okay, so like this, these many slots will be there. Inside that you will be having either 0 or 1 or 0 1 0 1 0 1 0. Okay, so let's assume you are inserting 10 in that. Okay, so I'll show you how this would look like, but you don't know what is the binary of 10, right? So let's assume you are inserting this 5 in that. Actually the binary of 10 is 1 0 1 0, but let's not talk about that because we are working on this one. So let's suppose you are inserting this 5. Okay, so how it would look like in your memory? There is going to be 0 0 0 0 0 0 0 0 32 bits. So again our this 5 will come here. So this is how it is going to store in your memory. There is something called little indent and big indent. I won't be confusing you a lot because if I'll start talking about little indent and big indent, this will get messy, because in one style this start from here, and in another style this will come here and consecutive zeros will come here. So for simplicity I'll keep it like this only, and I won't talk about little ending and beginning. We'll talk about in future coming videos if we'll require. Okay, so for now you just think like, if you are writing integer v is equal to not 10, like 5 here. Okay, so this 5 is going inside your v, and this is like this. Your v is in your RAM looking like this. Okay, you might be thinking, why these many zeros are there, then at last it is getting 101. Yes, because we can store 1 lakh, right? 10 lakh, 20 lakh. So as we will increase our value, these 1010 mixing will start coming here. Okay, so the maximum number you can store in integer is some number, I don't remember that, but here it will be like 1 1 1 1 1 1 1 1 1 1 1 1 all the way 1 only. Okay, that would be the biggest number, and the smallest number is 0 0 0 0 0 0 0 all the way 0 up to 0 here, which is nothing but in decimal if you will talk about, which is 0. Okay, so this is how things get stored in your RAM. So I was talking about shift, right? So this is our left shift. Now you are ready to understand what is left shift here. So as you know, this is the representation of your decimal number 5. Okay, this bit representations. Now if you will left shift it, so let's try to understand it. Like, you are performing some operation like v, which is your 5, which is having this bit representation, with left shift by 1. For simplicity, we'll think about this 1 first. So this whole bit representation will get shifted by 1. So this 0 will go here. So if it is going here, this is getting lost. Okay, because this is the boundary. Okay, so this particular 0 will come here, this 0 will come here. So it is taking one left shift. So as it is left, it is going inside this direction. Okay, so this 1 will come here, and this 0 will come here, this 1 will come here, and there is this empty space here, right? Because this particular 1 will come here, so there will be this empty space. And always remember, empty spaces are always get filled with zeros. So in short, I will take this snippet to explain this left shift. So let's assume you are having this 0 0 0 0, this one, and one more time 0 1 0 1. So this is this memory area. Rest are 0, so we should not take care of that because it will take so much time. So let's suppose here this 0 is going here, this is going here. So the left shift of 1 on this binary representation produced like this: 0 0 0 0 1 0 1 0. So remember this, I told there will be this empty space after this 1 will get shifted here. So this empty space is getting filled with 0 here. So this would be the result. Okay, so if you notice here, if you know, this is going to produce 10. Okay, because binary representation of 8, 9 and 10 is 1 0 1 0. Okay, so it is like this: 8 would be 1 0 0 0, and 9 would be 1 0 0 1, and 10 would be like 1 0 1 0. Okay, so that's why it is producing 1 0 1 0. That's why if you will print this expression like C out, this is going to print 10 for you. Okay, so let's check this. This is very interesting, right? So see, I have written exactly the similar what we saw here. Okay, so V is having 5 and we are giving left shift. This is the left shift operator here by 1. Okay, so this is the syntax of writing that, and whatever the value is coming, we are just simply printing that. Okay, so let's print this V also. It will be very easier for us to understand. Okay, so let's print this. See, this is 5 and another one is 10. Okay, so as I told here, it is representing 10 here, so it is giving you that. So this was about left shift, and you are shifting it by 1 only. If you want to shift it by 2, you just simply shift it by 2 here, and we'll see the result. What is that? By just shifting it by 2. So first try to understand it here. Like if you will shift it 2 times, then this is the result of 1 time shift. Again, if you will shift it one more time, it will be like 1 0 1 0 0, and here 3 times zeros. So this is I don't know. So let's calculate this. So we'll learn something new today. 0 0 0 1 0 1 0 0. So how to calculate the decimal of this binary here? So I'll tell you one rule. This place is 2 to the power 0th place. This place is 2 to the power 1. This is 2 to the power 2. This is 2 to the power 3. And this is 2 to the power 4. So we will consider whatever is 1 here. So this is not considered, this is not considered, this will be considered, this is not considered, and this will be considered. So what is being considered? This one and this one. So we'll add this. So 2 to the power 4 is nothing but 16, and this 2 to the power 2 is 4. Okay. So 2 to the power 2 is 4. So add is 20. So this is 20. So this is how we calculate this. Okay. So this number is producing 20 here, and this was 10. This was 5. Can you make out any pattern here? So the pattern is, I'm going to tell you that, just listen it very carefully. So the pattern is, whatever the number is you are going to shift it, if it is one time shift, it will get double. Okay, like 5 to 10. If it is again one more time shift, it will again get double. Then the current value, I mean with the current value, okay, not with this 5. See, one time shift 10, another time shift 20. If you will shift it again one more time, this will become 40 here. Okay, so like this it will work. And the same scenario is for right shift also. So if there is this right shift operation, then the only difference would come here is, instead of left shift, you will be writing right shift. Okay, so we'll remove this. So instead of left shift, you will be writing right shift here. Okay, so whatever is there in V will get shifted by right, and whatever the value you will be giving. So as this 0 was going and getting discarded, now this time let's suppose if your V is this initial position 5. So let's take the example here. Sorry for not removing everything here, I'm so lazy. So let's suppose we are shifting right time. Okay, right side I mean. So the bit pattern is like 0 0 0 0 0 1 0 1. This is nothing but your 5 in decimal. So if you will right shift it, this is the boundary we all know. So if you will right shift one time, this would look like this: 0 1 0 0 0. So that's it, you are done. This one will go out and get discarded. Okay, and I told you, as this is going this way like this, one empty space will come here because this 0 is going here. Okay, and this 0 is going here, and this 0 is going here. So in last there will be one space. So that space is always getting filled with zeros only. Okay, I told you here, right? So this is going to be your result, which is 2. Okay, and if you will again right shift it, it will be like 1 and then 7 zeros: 1 2 3 4 5 6 7. Okay, so this is going to be your again one more right shift on this one, I mean this 2. So this is going to represent 1 here. So there is another one pattern here. If you are doing right shift, the value is getting divided by 2. So 5 divided by 2 is result 2. I mean it is 2.5, but we don't consider point values. Okay, so if 2 is divided by 2, result is 1 here. Okay, you can see this. And if 1 is divided by 2, which will produce 0.5, and as we don't take decimal numbers, floating point numbers, we will be ending up taking 0. So as you can see, if we will make it one more time right shift, this 1 will go here and got discarded. So the result will be 0 0 0 0 0 0 0 0. Okay, so like this it will work. I think I have not messed it up so much. So let's quickly see the programs for all these operations. Okay, so let's first learn about this bitwise AND operator. Okay, what we learned first. So as we know, this would result into binary operations. So let's run this one. So this operation would be like 2 is nothing but your 0 1 0, and this 3 is nothing but your 0 1 1, and there is this AND operation, and we know the rule. If there is 1 0, the AND would be 0 only. So 1 1 1 0 0 0. So this is 2 only. See, this and this both are equal. So this is producing 2. So the answer for this one should come as 2. So let's check that. See, the answer is 2 here. Okay. So this is how we do the AND operation with these numbers. You can have variables also in place of these two numbers. For simplicity, I am keeping it like this because this video is going to be very long video otherwise. So let's check this binary operation for this now. This would be like again 0 1 0 and 3 is 0 1 1, and this time we are going to operate on OR operator. Okay, so OR is like if anyone is 1, the result will be 1. So this is 1 and this is 1, and both are 0, so the answer will be 0. So this is nothing but your 3 here. So the answer for this should be 3. Let's check that. See, it is 3 now. Okay, so this is how it works. So the XOR is, it comes with 6 number on your keyboard if you're not able to locate it. XOR is something like this. This is 2 0 1 0, 3 is 0 1 1, and we are applying XOR, which is nothing but when both are different, then only it will produce 1. So these two are equal, so it will be 0 0 0, which is equal, so it will be 0. Okay, so this is going to produce 1. So here this expression should produce 1 here. Let's check that. See, it is producing 1 here. Okay, so this is how this XOR operation work, and we already saw how this binary left shift and right shift will work. So let's give it a try here. So for simplicity, I'll shift this 1 3 times. Okay, so don't forget the placement here. Left hand side is always your operand. Okay, what you want to operate with, and how many times that shift should be is coming on the right side. Okay, so if this is the situation here, this would be like this. There is this 1. Let's suppose we are talking about this 1 with 4 bits only, because no need to write whole 32 bits because that would be very long. So if you are applying 3 times left shift, so left shift is this one. So this 1 would come 1 shift here, second shift here, third shift here. So this would be like 1 triple. So this is nothing but your 8. So this expression should produce 8. So let's check that. See, it is producing 8 only. Okay. So the same thing will work for right shift also. So in this case, if you are shifting it left side, this is going to be 8, and if you are shifting it right side, this is going to be 0. Why 0? First, let's see the output here. See, it is 0, and the reason would be like we know how to write this 1. Okay, so this is the binary representation of your 1 with, assume you are having this 28 bits as zeros. Okay, here. So this is how it would look like, and if you are making it right shift 3 times, so as we know, this is like this whole boundary. If you will make it 1 shift, this 1 will get lost here. So everything is 0. So it doesn't matter how many times you do right shift and left shift, zeros are always zeros. Okay, that's why it is producing 0. Okay, so that's it. I think I made this video so long, so if I bored you, so sorry for that. But if you think you learned something, hit the like button and share this video with your friends. So I'll see you in the next video. Bye bye.